Hi, everyone. Anybody have any questions before we get started?
Yes, I have a question, Professor Younger.
Yes, sir.
What is the next test going to be covering, and when is it going to be?
We should have another one on Friday. That one should cover, let me double check my syllabus. Actually, I don't know if I even can. Let me see. So if I had it up already. Crap. Of course not. Let me double check. Let me see. I did not mean to go there. So the next one is, of course, Friday. And I'm trying to scroll to that spot right now. Yes, and that one is supposed to cover basically 24.1, 24.3, 26.1, and 26.9, or 26.1 through 26.9. Let me double check what they are, just because there's so many chapters we're going through so quickly. I don't know all the chapters off the top of my head. So the 24.1 and 24.3 is the oh yeah, that's Huygens principle. Diffraction, Young's double slit experiment, and then the 26.1 I think is relativity. Yeah, 26.1 through 26.9 is relativity. So that's all what's occurring on this Friday's test, but that's a online test, so it'll appear Friday, but you'll have at least until Monday, but probably till Wednesday to get it finished.
And then for the when is test 5 going to be fit in somewhere?
Test 5, I don't think I'm going to do one. I think I'm just going to, since the semester's gone so fast, rather than make the final like I normally do, even though the syllabus didn't say it, I normally make the syllabus comprehensive. Probably the final is going to cover basically everything from from test 5 on the syllabus through what the final exam says.
Right, and I had another question on that. So for the final exam, it says 30.1 to 30.9, 31.1 to 31.4. So does that mean it's not going to be covering anything from chapter 32 or 33?
And what do we do with 32 and 33? I don't even remember if I cover 32 and 33. Probably. Oh, yeah, that's right. Yeah, I think I cover that material just because it's stuff that an educated college person should know. But I don't think I'm going to actually test you on it. Let me see. 32 and 30. Yeah, it's elementary particles. Nah, there might be. Well, let's put it this way. I'll give you a practice test and you'll see how it divides, but it would probably be very few questions from 32 and 33. I don't know why. I'm thinking the reason he didn't put it on there is because this semester that he did this, we ended up losing material because that was the end of the semester where we had the quarantine stuff. So
Okay.
normally what would have happened, that would have probably been test 6, and then the final exam would have covered that 32 and 33. I'm probably going to put something in 32 and 33 on it, or we only got 2 weeks, so really there's nothing else we can do. So yeah, I'm just going to have to say 27.1 through 33 will be what the final exam is, and that's going to be pretty big. The good news is when you have a test that covers that much stuff, I can't go very deep in anything. So
Okay.
it should be an easier test, if you will.
Okay. Thank you very much.
No problem. Anyone else? We're up to 21 people. Overall, the test grades varied a lot. I've got to make up a new one because I think some student got knocked out and ended up getting a single-digit score, but I think it's because they got knocked out. But we had, I think, seven A's, so that's pretty good. The class average was right around the low C end, which is also quite normal. I know all of you are probably used to making better grades than what you made on that. I got several emails saying that. I would just advise you that I give you all those extra amounts of time when you take the online test, and I free up your resources so that you can Google answers and all that stuff like that. And basically I do that because I know that if I say you can't do that, someone's going to do it anyways, and it's not fair to those people that are honest. The deal is, the more you're using that, the less you're learning. And in your college career, everything you cover should be stuff you're striving to learn, not striving to get through. If you're striving to get through it, it's not a very good way of living or learning. So not only that, it becomes really easy to do that even in your classes that ultimately become the ones that are important. Like if your major happens to be, history or something, all of a sudden you find shortcuts in your history classes too, and then you get somewhere where you have to actually express your knowledge of history, and you find out, well, I don't know anything, right? So anyways, just try to keep that in mind. Only got one more test that's going to be like that, but each one does count 15%. So that's somewhat of a deterrent, but I know you guys can do it, because like I said, we had like 7 A's, and then I mean really high A's in several cases. So good job those who did wonderful, those who didn't do wonderfully. Well, what I'll tell you is, if you didn't do as well as you normally did on this test as you did on the online test, let's just try to make the next one better, and maybe Mr. Younger will find a way to help you guys out. Okay. How about any other questions?
I was wondering if the grade cutoffs for like each letter grade are, or is it like 90 and above is an A, 80?
I do 89.5.
Okay.
And usually for the C, I usually drop it down to like 68.5 instead of 69.5. So I don't, I try not to kill people. I try not to, most people that take 202 are not majoring in physics necessarily, but they are related to something that needs science. So I can't let them go scot-free without learning science in some sense. But at the same time, I don't want to ruin their life by giving them a bad grade. So ideally, I'd like you to be able to transfer it, which means that you really need a C. So I do my best to help you guys, I promise. Anything else? Maybe we can make a deal. I think y'all can still see the test. If not, I'll go back into it and make sure y'all can see it. And I did make it where you can see the right answers. Was everybody able to see the right answers? Or did anybody try to see the right answers?
I didn't see any right answers.
Yeah, basically they came up like right after the time that the test was allowed to be accepted, which was like 12:20, 12:30, something like that. But I think I put it up for a finite amount of time. So if you didn't look at them that day, you wouldn't get to see them. The final correct answers are on there. I'll make them where they're available to you. I think what I might give you a chance to do is let every one of you who say scored less than an A, if y'all want to redo that in its entirety, you've got the right answers, you know what you're trying to work for. Show me step by step, take photographs or scan pages or whatever of your work, and do each problem neat and orderly so that I can easily read it. And maybe I will make you a deal where if you score better on the second test, I'll give you the higher of the two. So something like that, just to give you another chance to say you haven't shot yourself in the foot. Okay.
And when would you want that by?
Let's say by Monday.
Alrighty.
All right. So do that. Figure out how to do those problems correctly, and maybe that'll help you guys out. Okay. Like I said, I'll figure out some way to help you. I think the bare minimum would be allowing me to replace your midterm grade with your final grade if it's higher. I won't go the other way. I'm not gonna. If you do worse on the final, I'm not gonna give you the higher of the two that way. Okay. But if you do better on the final, I'll definitely give you the higher of the two for both of them. Okay.
So are we gonna redo this test? Like, will it let us like do it a second time, or do you want us to do the questions that we already had, and then
The questions that you already had, and everybody had the same questions on this one.
Oh, okay.
So the same questions, and even if you got them right, I want you to do them anyways. So I want you to redo all of them,
Right.
answer all the concept questions in order. If it helps you, take a screenshot of the actual question and put that in there, because I don't want to see just answers without the question, because I need to be able to read the question. I don't flip back and forth and I don't memorize questions. So when a student writes up a homework or a answer for me, I expect to read the problem in its entirety and then see their work for that problem, so I don't have to flip back and forth between the tests and it. So even if you just have to take a snapshot and stick it in a Word document and then print out the Word document and solve it on a piece of paper and then take a photograph of that, that would be fine, as long as I can read the question and then the answer and then the next question and then the answer and the next question, then the answer.
Okay.
Okay.
Doing 27 to 33 for the final.
Yes, 27 through 33. And like I said, it'll be light on 32 and 33.
Okay.
I might even lean towards more of the conceptual questions than the actual, and you'll see when you get to 32 and 33, you'll see that there's questions are generally not much calculation stuff. I mean, the calculations that you get you to do are very easy. The big thing is the concepts, like we're going to learn about the Big Bang, what evidence made us reach the conclusion that the Big Bang occurred, as opposed to, a lot of people will tell you that basically the Big Bang was, discovered in the depths of hell to try to turn you against God or something like that. And in actuality, Lemaitre was a Jesuit priest, and he was the first person really that anybody knew of that predicted the Big Bang. And then Hubble, who also was a Christian, came along and found evidence that supported the Big Bang, even though he didn't know anything about Lemaitre's predictions. So it's kind of neat. It's just those two chapters are very interesting. The elementary particles I find less interesting, but the cosmology, the Big Bang, expansion, that kind of stuff is really pretty tight. It's cool stuff. So, any questions about anything else? All right.
Anger.
Yes, ma'am.
Would you be able to go over the grade breakdown again?
Yeah, it was. I think I said we had 7 A's. Are you talking about where the
percentages?
Okay, gotcha. Yeah, 89.5 is a A or higher. 79.5 is a B.
It's actually like how much tests there were, things like that.
Oh, that thing. Gotcha. Okay.
Yeah.
Let me pull back to the syllabus then. I think I got it right here. Yes. Okay. So what I changed was, remember the midterm and this and all these things, they added up to be 20 point or 10 points short. So what I did was I put 5 points in tests and 5 points in your problem. So now your tests are worth 25%. Your midterm and final are each worth 15%. And your homework problems is worth 20%. Your conceptual is worth 5%, and your lab's worth 20%. Y'all, I know y'all are stressing about your grade right now, but that you will be surprised at how helpful this 20% lab grade is.
Are the labs graded already? Because I haven't received anything yet.
Yeah, I graded them. I'm trying to figure out what's going on. It's like I graded them, and I don't want to regrade them. That's the big problem. But for some reason, it's not showing on this side. So I'm thinking there's something I've got to do to sync my app to the actual Canvas, because I did it all on my phone, which that was the way I could do it, quickly. But if not, I'm going to have to regrade them again. And I say all of them. I actually graded the first 4 labs. So hopefully I'll get that problem settled today. I'll send you an email when the grades are actually posted, but I don't think I recall anybody going less than a 90. I think a 90 might have been the lowest score I saw out of all of them. So y'all can imagine you're doing really well. Okay.
And I have one more question.
Yes.
So on Canvas, it does give us an estimated grade. Is that in any way, shape, or form correct?
This one, I think I've got all the percentages correct now. So it should be accurate. I'll double check today though, and I'll let y'all know for sure. Okay. I've got it set up where it's supposed to be accurate. Of course, right now it's basically pretending like you haven't done anything related to labs. So it's not even taking lab into consideration. So your grade's actually going to be quite a bit higher than that, but I'll double check, make sure all those percentages are right.
And it also has like the practice tests graded and stuff, but I'm sure
I pulled those out. Those are not supposed to be in there anymore. And in fact, let me look at something real quick again on another screen. I'll talk to you about it as if you're seeing it, but I know you're not seeing it. Let's see here. students get really lost when I give them the assignments, so I don't make the assignments available. But when I look at the assignments, it tells me exactly which thing each percentage is counted for. So, oh yeah, so yeah, it's not doing it correctly yet. But the practice tests are separated, so that should make it where your practice tests are not counting against you.
Okay, and didn't you say if we took it a bunch of times and did pretty well on that you were considering giving us like an extra point or two?
Yeah, well, it's normally one of those things where if you're near the next grade, in other words, like you're really almost at the A level, maybe you're a point shy of really being an A, or even a point and a half, 2 points. And I look, and you've been taking a bunch of practice tests and actually taking them seriously, meaning you scored like a 70, 75 or better several times.
Mhm.
It's statistically unlikely that you can do that by just randomly putting in answers. That's why I choose that grade.
Yeah.
Then I usually will give you the 1 to 2 points.
Well, I don't mind announcing it. I got a 78, so would you consider maybe bumping it to an 80 because I took the test like at least 22 times, I'm pretty sure.
Oh, so no, what I do is in the end of the semester for the final grade. So it's
Okay.
a way bigger deal than what you're
Oh.
thinking. I actually do it
Oh,
for
yeah.
the course grade, not for an individual test.
Okay, gotcha. Okay, thank you.
And that 78, by the way, is not bad, guys. I want to tell you the way physics and chemistry courses work in colleges and universities, the 200 and the 100 level tests, a typical average is in the 50s. So when you score in the 60s and 70s, you're probably right in the middle of the pack, if not through the high end of the pack. So that's a good sign. We want everybody to be, the top, in the 75s. That's our ideal scenario with final exams and midterms and tests and stuff like that. But generally speaking, I've been to some premier institutes and have not found that to be the case. I taught at NC State, I taught at Chapel Hill. I even took a class at Duke, and everywhere I went, we found that was the same problem over and over again. So chemistry and physics departments often do not have test averages in the 70s. The only places I've seen actually where it's like that is places where the schools are not challenging their students enough. So don't feel bad, guys, if you're pulling like a 70 or something. It's ideal if the instructor lets you know what the test average is, and always compare yourself to that. And then just be prepared, because I've had students before. It's like, well, I'm pretty sure I'm well above average. I'm a hard worker, blah blah blah, and then you find out, well, no, you're doing about average. So sometimes that hurts your feelings, and it might just be not your subject. So it's all good. Yes.
Well, I just wanted to say that you're a really good physics professor, and that none of the ones at my school were anywhere near as consider or good about the material that you're teaching, because basically at my school, getting like a 55, they have to. That's equivalent to like a C.
Yeah,
it's really hard.
Yeah, and it scares people, especially pre-med majors. Yeah. Well, thank you for that, JC. I appreciate it. I try, and that's sort of the good thing about community colleges. Most of us are here because we really want students to learn. We love our subject, and we're not as interested in advancing knowledge as much as we're interested in advancing the knowledge of how to teach properly. So, but thank you very much. All right. Well, I guess we should get started on our new material. Since I paid JC for those kind words. Oh, I forgot to tell you. No. So anyways, we're going to finish off chapter 30. I went over all the decays. Remember, we talked about alpha decay, beta decay, which also included electron capture. So you should be able to know how to complete those reactions, meaning if you see, the reaction on the left, or the input on the left, if you will, and then the products on the right, and they'll inevitably have one of the numbers or the whole thing missing on the product side. You should be able to use conservation of atomic mass number, basically atomic nucleon count, conservation of charge, to figure out what those numbers are. So make sure you can do that kind of stuff for the alpha, the beta, and the gamma particle decay. So that's what we covered so far. The remaining stuff we want to talk about is related to one of our labs, and it's half-life and rate of decay. So what we're going to do today is we're going to talk a little bit about how decays occur, and it's something that's used frequently. Then knowing that these elements are, for instance, radioactive, you can actually use them. So, for instance, I have a something called GERD, that's gastroesophageal reflux disease, and one of the ways they determine that you have that is they want to rule out that you don't have some kind of blockage. So they expect your food to go into your stomach, and within a certain amount of time, all that food should have passed through your stomach and be in your small intestine, large intestine, all that over a certain period of time. Well, how would you figure that out? You know, so what they came up with is this really brilliant idea. They took technetium-99, which is a man-made isotope, meaning it doesn't naturally occur very frequently in nature, but you take regular technetium and you bombard it with, I think they do it with neutrons, and you make a basically a metastable version of an isotope, and it has a half-life of 6.01 hours. And it's not toxic to people in general, but you know, obviously it's irradiating you if it's inside of you. But they take it and it's like a little salt. They've got it, you know, this metal crunched up into little particles, and they would take an egg and they put it in a styrofoam bowl. They microwave and scramble the egg and pour the technetium on it like it's salt, and then cook it in the microwave, and then you eat it. And then the neat thing is, you lay down in front of X-ray film basically, because you're the radioactive thing. And they take the X-ray film, they rotate it around your body like this, and over time that the computer builds an image of what you should be seeing, because it's seeing in 3 dimensions by going all the way around you like this. And lo and behold, they can detect all the food in your stomach. They also, that's called a gastric gastric emptying study. And then they use technetium-90 another way. If you ever have a history of heart disease, or if you have some heart-related problems, there's a thing called a nuclear stress test, where in this case, they take the technetium, they mix it in a liquid, and they shoot it directly into your veins. And they do that, and then they get you basically in front of that film again, and the film rotates all around your body and all this stuff. And they look and see if any places in your heart are not getting that technetium-90, because the technetium-90 is a radioactive source. So it's shooting out all these gamma particles basically. And if some part of your heart's not getting ample blood flow, there'll be like a dark spot on your heart. So that's a good way to look for a blockage. But then they amp it up a little bit, because your heart does different things and behaves quite differently under exercise. So then they put you on a treadmill, and you run on the treadmill. They give you another dose of the technetium, or actually sometimes they don't even have to do that. They run you on the treadmill, get your heart rate up, and then they film it again and see if now there's any dark areas. Well, the neat thing is the technetium-90 only has a half-life of about 6.01 hours, but that's still not a safe thing. So like when I had my nuclear stress test, I just had my youngest daughter, and I couldn't hold her. She was, you know, an infant, and I couldn't hold her for 48 hours because I was radioactive. And like, it was really neat to me, because I you know, went home, I took a Geiger counter with me, and I was like, hey, look at this, honey. So it's some pretty neat stuff that comes from this. So I think y'all enjoy it. Just knowing all the different things that we can do. Obviously, they use radioactive sources for treating cancers. I've already talked to you, for instance, about the Bragg peak for protons as opposed to electrons or photons. Those Bragg peaks are really what, and that's BRAGG, and then peak, PEAK. You can Google those if you'd like. Those Bragg peaks allow you to basically adjust the energy of the radiation that they're shooting at you until the peak is right in the center of the tumor that they've discovered. And then they adjust it again for another angle, because sometimes it might come straight in, and maybe there's only that far between your skin and the tumor. But other times they might come through your back, and it's that far between your skin and the tumor. So you adjust the energy where the peak is way up there, and they shoot from the behind, and then they shoot from the side and all the different ways, so that they minimize the radiation damage to all the adjacent tissues. In doing so, you end up getting a much better treatment and much less harm. A good friend of mine, Mardell, I might have mentioned to you, but basically she had breast cancer when she was quite a bit younger, and I think she was in her 50s. But she just laid against the atomic accelerator that we use in the research lab, basically, and she laid against it, and she had horrible burns for months. because that was the only way they could do it back then. So we're definitely coming along, and the knowledge of radiation has helped us infinitely. It's introduced some bad things that could really be bad. I mean, you probably heard the dirty bombs. You already know about nuclear weapons. So there's some bad aspects, but there's also some amazing aspects that allow us to cure people of horrible diseases. So let's get started. I'm going to share my document cam. Does anybody have any questions on anything? And it could be related to that medical stuff. I did my master's degree. I was at an institute that offered medical physics PhD. So all of my seminars were PhD related material for medical physics. So I have a little bit of knowledge in that area. So if anybody has any questions, I might be able to answer them. All right, so it turns out that basically if you try to talk about how particles are going to decay, what you'll have is this sort of you'll have like let me get this thing focused a little better. There you go. So if you have this nucleus that you know is radioactive, meaning it's unstable, it's going to decay into something, okay? The problem is that's a random event of when it's actually going to decay. There's no variable that we could watch to see, oh, here it goes, it's getting ready to decay. It's sort of like a tidal wave or an earthquake or something like that. We haven't found any way to know the precursors of it, and we don't think there is one in these cases, whereas there might be some in those other issues. But in the case of radioactive decay, we just think it's a random event. But being random also means statistics work really well. So what we do is we say, well, it turns out that the total change in the number of nuclei, so N is the nucleus, say, or is a particular nucleus, and if you're wanting to count the number of nuclei present, at any one time, N would be the number present, but delta N would be the N final minus the N initial. In other words, how much that's changed by. Well, the nuclei that you have is radioactive. So when it decays, it's going to decay into something other than that nucleus. So you're actually losing them. So this number has to be definitively negative. Well, we think that this number, this change in nuclei, is directly proportional to the number of nuclei present. So you put an N there. That means if you have a billion nuclei, then you're going to get a certain delta N. But if you have 2 billion nuclei, then you'll have twice as many delta N's. In other words, twice as many disintegrations happen for a given unit of time. Maybe you watch it for, say, 1,000 years. And in 1,000 years, you found that 1 billion nuclei decayed once. Now, if you do it for 1,000 years again, but instead of having 1 billion nuclei, you have 2 billion nuclei, then probability says that you will get twice as many reactions, i.e. you'd have 2 disintegrations in that 1,000-year period. But we also know the longer you watch it, the more disintegrations will happen. So we also say it's directly proportional to the change in time. So this is just a statement of proportionality. In order for it to work, we still need a constant, and that constant is what we call lambda, and that constant we actually call the decay constant. So this lambda is a decay constant, and it changes from material to material. So in other words, this thing is what makes it based on a certain nucleus. This just says for any nucleus, you're going to get a change delta N that's proportional to the number of nuclei and the length of time you watch it. This is the part that dials it in and makes it about uranium or plutonium or technetium-99 or nickel or whatever, okay? So that actually turns out to be that the rate of decay, the number of disintegrations per second, delta N over delta T, is actually equal to negative lambda times N. And this is not unlike Newton's law of cooling, where it says the change in temperature is per unit time is directly proportional to the temperature differences, something like that. This actually is solved by a very typical equation. In other words, we could change these to derivatives and then do what's called integration, and out would pop this number. And it says basically that the number of nuclei you have at some time t, so you might even write a n of t, like a function. It's not times t, it's just a function of t, is equal to n0, the number of nuclei it had at t equals 0, times e to the negative lambda t. So that's the actual expression. This is what you're going to use to calculate the number of nuclei present and stuff like that. Of course, you could also maybe not care about the number of nuclei present. If that's the case, maybe you want to know about the rate of decay. And the rate of decay, R, is defined to be the magnitude of delta n over delta t. And in actuality, it's going to be something that you're going to have to make positive. So that's why we're using the absolute value bars. And that's going to be the radioactive decay when t equals 0 times e to the negative lambda t. So those are the two major equations you're going to use. You've probably heard carbon 14, for instance. Anybody know what they do with carbon 14? Anyone have an answer? I'm going to check the chat just in case someone's typing it up there. Nothing yet. Carbon dating. Anybody ever heard of that? Well, when we talk about those things, there you go, date fossils. Yes. Carbon 14, for instance, I think it has a half-life of 5,730 years, I think. It's either that or 80 years. I can't remember, but it's definitely, a long time span. And you can use that to date fossils up to a certain age. The rule of thumb is definitely 3 half-lives. You can get some really good results. And if we're really, really specific about it, we might be able to get 5 or 6 half-lives. So if you assume 5, let's assume 5 just for the heck of it. 5 times 5,000 would be 25,000. 5 times 700 would be 3,500. So about 28,000 years, roughly up to 30,000 years is about all you can date fossils with carbon 14. But you can do the same process with other isotopes. So that's kind of helpful. The reason why carbon 14 is so helpful and why it points to the time of death is if you've ever learned in biology about the Krebs cycle and all that good stuff and the processes that go on when you actually breathe, you'll know that while a creature is living, it takes in the atmosphere that it lives in. So it breathes in oxygen, mostly nitrogen, of course, but all the other things that are in it. And some of the things that are in it is, in fact, carbon and carbon dioxide, for instance, or even carbon monoxide, but majorly carbon dioxide. So when you breathe that stuff, you're constantly getting the carbon in your body replaced with new carbon exactly in the percentages of isotopes that they had at the time. So when you die, you stop breathing and you stop getting new supplies of that carbon. Therefore, you're slowly going to lose the radioactive isotopes of carbon that you breathed in after you die. One of those isotopes happens to be carbon 14, so it's automatically already in your tissue. So you can look for the amount of carbon 14 in there. And if you know the conditions of the atmosphere at that time, which we have other ways of knowing, then you can very accurately predict how long the thing has been dead. So that's how carbon dating works. But like I said, we use plutonium, well, not plutonium so much because that's man-made, but we can use uranium and all sorts of cool stuff like that. To date things to even longer ages. For instance, we use rocks that have hit the Earth from Mars or rocks that have hit the Earth from outer space. We use comets, debris that we find in space. All those things we can date, and when we date them, we find that our actual solar system is probably about 4.9 billion years old. So we have things that can even have half-lives on the orders of billions of years old that we can use. So now we're up to this. We have the number of nuclei present at a time t, and I could write this r of t as well. I just wanted to put it there at one time so you realize this is a function of time. But the number of nuclei at time t is equal to the number of nuclei you had at time t equals 0 times e to the negative lambda t, where lambda is that decay constant. The rate of the nuclear disintegration, that's like the number of decays per second is what the units would be, is equal to the decay constant at the very beginning, or not the decay constant, but the rate of decay at the very beginning times e to the negative lambda t. So you can see in both cases, basically your graph is going to look like this. Okay. where this is either R0 or N0, depending on whether you're graphing R0, or excuse me, whether you're graphing R or N. If you're graphing N, that constant will be N0. If you're graphing R, that constant will be R0. And basically it goes down by 1 over E for each amount of time, 1 over lambda. So if you want the actual half-life, you'd say, okay, well, at what time does delta N equal 1/2 of N0? Okay, R, since we're now dealing, instead of this, we're actually dealing with N of T. If we want N of T equal to 1/2 N0, and we want to say T is equal to question mark, that is the definition of the half-life. So the tau, the half-life, is equal to the amount of time it takes to go from N0 nuclei to N0 over 2. So if I did that, came down here, then this would be tau 1/2, or just plain tau. I think your book is using tau, or no, your book is actually using T 1/2. So that's another way of writing it, T1. Oh yeah, that's right. I should probably not use tau. Scratch that tau out, everybody. I forgot your book is actually using tau for the mean lifetime. So we'll call it T 1/2 is the half-life. Well, what that means is you take 1/2 N0 and put it on that side, and that's equal to N0 times e to the negative lambda t. You now see that the N0s cancel out, and the way you solve for an exponent is you take the logarithm of both sides. In this case, I'm going to take the natural log because then I don't have to deal with some stupid numbers. So I'll take the natural log of 1/2 and set that equal to the natural log of e to the negative lambda t. You might remember your laws of exponents that say basically when you take the ln of something raised to a power, you get the power times the natural log of the base. And similarly, this is the same thing as negative ln to 2. So I'll say negative ln 2 is equal to negative lambda t ln e. Now the ln of e means, remember, here's the rule for that'll help you for just about everything when you're dealing with logarithms and exponents. Y equals log base b of x implies x equals b to the y. So right here, I've got a log base e. That's what the b would be in the case of the ln. Its base is e. So really, when I say y equals ln of e, I am writing the equivalent of basically y or x. Notice the x was what was in here. So I'm saying e is equal to e to what power? That what power is what y was, right? So what must the ln of e be? Can anybody tell me from that? If e is equal to e to some power, and that power is the value we call y, which is what the ln of e is, what must y be? Or alternatively, does anybody know what this answer is? The ln of e. It is 1. Okay. So this is mathematically why it's 1, because this rule always holds. If you say something is equal to a certain logarithm of a certain base of a certain value, then what you're really asking is what value y do I raise b to get x? So what value do I raise e, in this case, because that was the base, to get e? Well, the only value I could raise e to get e is e to 1. So y is 1. So now I've got that. So what this tells me is, notice I can get rid of the negatives on both sides. And I'll say that ln of 2 is equal to lambda times t. And lambda times t, remember, t is technically the half-life, because that's the way I set it up. I was trying to solve for half-life. So that t has to be the half-life. So what I found out is the half-life is equal to the ln of 2 over the decay rate, which is 0.693 over the decay rate. So once you find lambda, you can easily find the half-life, and the half-life is just 0.693 over lambda. So that's another thing that comes in handy, but obviously you have to know what the lambda is. However, you can also flip this around and realize if I'm given the half-life, then I automatically know lambda. So you could also say, wait a second, lambda must equal 0.693 over T1/2. So if a problem gives me the half-life, then I can figure out what lambda is. So that's another way of looking at it. If you want to know the mean life, and that's basically the average amount of time that a nuclei will live before it actually decays, then that mean life, which is why I had to switch from tau up here, that mean life turns out to be basically 1 over lambda. And of course, since lambda is equal to T 0.693 over T1/2, then that means this is the half-life divided by 0.693. And 0.693 is just an approximation of what the ln of 2 is. It actually goes on forever. So it's not a rational number. But the key point is you can get 3 sig figs by just using 0.693. Okay. So those are the major parameters you got to be able to use and understand and stuff like that. Lambda, the decay rate, lambda is the decay rate. The T1/2 is the half-life, and tau is the mean life. So a typical reaction that you might want to examine is, oh, and I just looked up, by the way, your book does say that carbon-14 has a half-life of 5730, not 5780. So my first instinct was correct. My second instincts were not correct. Anyways, let's go ahead and solve a couple problems. So let's take technetium 90, or excuse me, technetium 99. I think its Z is 42, and it has a half-life of 6.01 hours. Okay. And let's say that we have a 10-gram sample of that. So the mass of our technetium 90 is 10 grams. What I would like to know is how many nuclei are present. So I'd like to know N0. And I'd like to know N at T equals, let's do 2 half-lives. I mean, I think y'all can guess, you know, if after 1 half-life, the number of nuclei present is 1/2 of N0, what do you think the number of nuclei present after 2 half-lives would be? Anybody? So if there were 100 nuclei, and 100 is kind of too small to really use this equation efficiently, this equation requires N0 to be really, really large, but let's just pretend for a second that it's still accurate. If N was 100, N0 was 100, after 1 half-life, how many nuclei would there be? There was 100, now there's how many? Just spit it out, anybody. You folks not very interactive today. Half of 100 is?
50.
50.
There you go. So yeah, after 1 half-life, it'd be 50. Now, after another half-life, that'd be 2 half-lives total. It's going to go from 50 to what?
25.
25. There you go. So you expect about 25% are N0 over 4 is what would happen. So what I'd like to know is what is N0? What is N of T after basically 2 half-lives? So I wrote 12.02 hours. I'd also like to know lambda, and I'd like to know R, the rate of decay. Okay, so those are typical questions. I'm thinking I'm right. Let me double check to make sure I'm right about the Z for technetium. 97, atomic number Z, 43. Thank you. Thank goodness I'll check that out. So 43. So if I look on a periodic table and try to find the half-life, or excuse me, find the mass of the periodic table, then I'm going to look for Z equal to 43. And obviously I'm going to find the smallest tables possible because those are the ones that are not going to show me anything because they're trying to sell me all the other ones. Jerk faces. This one looks a lot better. Nope, that one stinks. Crappity crap crap. I'm going to check the back of my book. All right, technetium 43. Yes, so blah, 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 blah. It has a mass that they're going to pretend is 98.00, I guess. So M technetium is equal to 98.00. One way you can think of that is the atomic mass unit, U, right? But another way we can think about that is that's the number of grams in a single mole. Okay, so that actually is correct. That's the number of grams per mole. So if I take 10 grams and divide it by 98.00 grams per mole, then I'll actually get the number of moles of technetium-90, and a mole is 6.02 times 10 to the 23rd nuclei. So then I'll be able to figure out what the total number of nuclei is. So 10 divided by 98 gives me 0.102. And since I'm making up a bunch of sig figs, I'm going to only go out the 4 moles. So 10 grams of technetium is roughly 0.102 moles of technetium. That means that the number of nuclei is equal to Avogadro's number times that. So 0.1020 moles times 6.02 times 10 to the 23rd per mole. In this case, you can write it as nuclei per mole. And there's some wishy-washy things that are going on here. For starters, they only gave me 98 in parentheses. That's because there's a buttload of isotopes that basically some are man-made, stuff like that. So it's kind of a questionable number to begin with. But this number is really the weighted averages of all the individual types of technetium. So really what I'm calculating is, in some sense, the average mass of all the different types of technetium, whereas when you're doing this stuff for technetium for like a test, they're probably going to have essentially pure technetium-90 or very close to pure technetium-90. So it's not that accurate. But anyways, I'm going to take and multiply 0.1020 times 6.02. And I think that's actually 6.022 is the next digit, but it's times 10 to the 23rd. And that gives me that N0, which I forgot to subscript 0 earlier, is 6.14 times 10 to the 22nd nuclei. So that's close enough. I mean, you know, if it's 6.14027 and we're calculating 6.14028, it's not going to matter that much. And that's really what's going on by using this as opposed to looking in the table of isotopes and seeing what technetium-90 99 actually weighs. So I did a little wishy-washy there stuff just to go through it. In principle, you should probably go to the table B, the appendix B, but I was on the fly, so I just used that. So now I have N0, so that's one of the things. I'll write check there, okay? I was told the half-life equals 6.01 hours, but I really need to put that in seconds. So what I'm going to do is I'm going to take the fact that 1 hour is equal to 60 minutes, and 60 minutes, or 1 minute is equal to 60 seconds, and realize that 1 hour has to be 3,600 seconds. So I'll say 1 hour is 60 times 60, which is 3,600 seconds. And now I have the half-life in seconds. And I get 21,636 seconds is the half-life. Now that I have the half-life, which I already had, but I can now use that to calculate lambda, because remember lambda is 0.693 over T1 half. So I'm going to say, I'm actually going to use Lin 2 instead of 0.693. I think I am. Yeah, I am. Lin 2.
Professor,
Yes, ma'am.
is there a way you can make this like more clear? I'm really struggling to see what you're writing.
Oh, yes. Yeah, let me write this answer real quick, and then I'll handle that. .0000, that's 4 zeros, 32. Okay. All right. So first off, let me get it focused a little bit. So what I had was technetium 99 with Z being 43. Remember that 43 down there is technically redundant because the TC symbol tells you what Z is. But I told you it had a half-life of 6.01 hours and that I had a 10-gram sample. What I asked you was, what is N0? That's the number of nuclei present in the 10-gram sample. And I told you I sort of did a fast and loose way of finding out what this was, and it's not that accurate, but I didn't care that much because I'm dealing with so many nuclei. Being off a little bit is not going to matter, right? So that's why I'm using this mass. But I also wanted to know what the number of nuclei present after 12.02 hours was. That 12.02, and I know that's hard to read, is just supposed to be double the half-life. I got you guys to predict, like Wheeler taught. Wheeler said you never should solve a physics problem whose answer you don't already know. So I got you guys to predict roughly what that answer should be, and that answer should be roughly 1/4 of N0. But I also wanted to know what the decay constant is and what the rate of decay is. So far what I've calculated is N0. I did that by taking this mass, this molecular mass, or in this case atomic mass of technetium 90, actually just a plain technetium. That's where I was, acting fast and loose. And I divided the mass of the sample I had by the mass per mole. That gave me the number of moles of technetium. Okay. Now I know that 1 mole is Avogadro's number of nuclei, so the number of nuclei should be 0.102 moles times Avogadro's number, which gave me 6.14 times 10 to the 22nd nuclei. So that allowed me to get N0. The fact that I already knew the half-life allowed me to use this expression to get the decay constant. And that decay constant, lambda, was 0.000032. Now you can tell that unit should be reciprocal seconds, but I couldn't fit it in there. But you can pretend that's a s to the -1 power instead of the 5 that it looks like. Okay, we're running out of paper, of course. Did I clear that up for you a little better? I know that's at least holding it closer, you could read it a little better.
Yeah, thank you.
No problem. So now the other part that I have to figure out is what's the rate of decay. Well, the cool part is the rate of decay, we know what that is because we worked that out earlier. You could say the rate of decay is equal to just R0 times e to the negative lambda t, or we could use this much easier expression. Since I know what N0 is, I can actually plug that in and get my actual rate of decay. I'm trying to remember if I had that as N0 before. I thought I should have had that as N0. So this should be N0, by the way. It's actually true for any N. So if you want to know what the rate of decay is when the number of nuclei are N, then you use N there. If you want to know what the initial rate of decay is, then you put N0 there. That's what I'm trying to show with that little arrow. So our rate of decay, which is equal to the absolute value of delta N over delta T, which we showed was actually negative lambda N, but since I'm taking the absolute value, I'm just going to call it lambda times N. In this case, we're talking about initial, so I'm going to say N0. So I got rid of the negative because the absolute value bars, and I'm just going to take this lambda that I just calculated and multiply it by N0. And remember, this is per second. So N0 should be, or excuse me, lambda times N0 should be 3.2 roughly times 10 to the negative 3. When I pull that up on my calculator, it'll give me some more digits. So that'll be better. And that's not 10 to the negative 3. That's 1, 2, 3, 4, 10 to the negative 5th. Okay, and that's reciprocal seconds times N0, which we found was 6.14 times 10 to the 22 nuclei. And ultimately, when we multiply these two, we're going to get decays per second. So let's multiply those two, 6.14, 10 to the 22. And I get basically 1.97 times 10 to the 18th. And that's decays per second. So now I've gotten lambda and R. All of those things are taken care of. Now, this decay per second that's technically a unit we call a becquerel. So someone might call that 1.97 times 10 to the 18th becquerel. Or you might even use the unit of the Curie, and the unit of the Curie is abbreviated CI. The unit of the becquerel is indicated by BQ, capital B, lowercase q. But 3.7 times 10 to the 10th decays per second would be 1 Curie. So you could divide this by 3.7 times 1 to the 10th, and then you get the answer in actual Curies. Otherwise, this is decays per second, or you could interchangeably call it becquerels or BQs. Okay, so that's just some terminology to know in case you ever have to deal with any other types of reading and radioactive material, stuff like that. They use it for a lot of different things. If you're going into physical therapy, there's even things where they can use it for that. So it's not something that just automatically goes away because you're not majoring in physics, especially if you're going in the healthcare field. The last part that we didn't see is what was the number N at T equal 12.02 hours. Okay. Well, if you realize that N of T is equal to N0 times e to the negative lambda T, and then you realize that T1/2 is equal to ln 2 over lambda. So you could say, well, lambda is equal to ln 2 over T1/2. So you could say this is equal to N0 e to the negative, and I'm going to replace lambda with ln 2 times T over T1/2. Okay, so all I did was take the ln 2 over T1/2, which is what this was, and stuck that in place of lambda. Now I'm going to do another neat trick. When you multiply two things in an exponent, that's basically the same thing as raising a power to a power. So I could actually, in principle, call this e to the negative T over 2 raised to the ln of 2 power. But that's not that helpful. The main thing I'm going to do is I'm going to now say this is negative 0.693 times T over T1/2. The reason why I'm doing this is because I don't really want to mess with converting that to seconds and all that stupid stuff. So I know that this T is actually equal to 2 T1/2 So now I can replace that with T1 half, and I don't have to do any math. That's the main point. So now I got N0 e to the negative 0.693 times 2 T1 half over T1 half. So the T1 halves cancel out, and I'm just raising something to the 2 times ln 2 power. Okay. I know that e to the ln 2, you probably know what that's going to be, right? You can use that y equals log base b of x implies x equals b to the y if you wanted to. I'm going to say e to the negative ln 2. And lo and behold, I get 1/2 because of the negative. But if I want to multiply that by 2, I'm going to write e to the negative 2 times ln 2, ln of 2, and I get 1/4. In other words, by doing that, I automatically know the answer is exactly what I expected, 1/4 times N0. I don't even have to think about the number of nuclei. I just know it's 1/4 of what I had originally, which is what our conjecture was. So by doing the mathematics this way, converting the T to T1 half allowed me to work that out. So really, just to let you know, what I typed in on my calculator is I typed in e to the negative 2 times ln of 2, and that gave me 1/4. When I did it without the 2, I got 1/2. So e to the negative ln 2 gave me 1/2. So you can see now why the half-life really works to be what it is because we solved it that way. Any questions on that? All right, so really that is the last part of this chapter, chapter 30, that we're going to cover. If you're interested in medicine at all, or if you just want to be educated about the medical field, about carbon dating or any of that kind of stuff, so if you're going into geology, for instance, radioactive dating is something that's important. I would highly recommend you read the rest of this stuff, but I'm not testing you on it, okay? You might, again, because it's a pain in the butt to sort out all these problems, you might see them in practice tests and you might see them in homeworks. So in some sense, it's a little bit part of the material you're going to cover, but I will not test you on it, okay? So we're now in a position where we can jump into chapter 31, which is the last thing we're going to do today, but I'm going to give you guys a 10-minute break. Let's give you a 7-minute break. Let's be back at 10:40. Oh, never mind. It's already 10:34. Yeah, let's go ahead and give you 10. Let's give you 11 minutes. So be back at 10:45. I'm going to stay here for a few seconds, and then I'll turn off my camera and recorder. But you can ask me questions until I leave if you want. So everybody, meet me back here at 10:45. But feel free to ask me questions. Obviously caused a great deal of harm and death to people, so it's really sad in many ways, obviously. So anyways, we're going to talk about that, and I was just looking at the sections. Yeah, they even go into human exposure of radiation, that sort of stuff. So let's go ahead and get cracking on that. So chapter 31 is called Nuclear Energy Effects and Uses of Radiation and stuff of that sort. So it turns out, you probably heard about in the time of Newton and before Newton, everybody was looking for the way to turn lead into gold. Well, guess what? We can do that now. We can turn lead into gold. It's called nuclear reactions. Okay, you can transmutate. That's the word for it. You can actually transmutate one element into another, and of course lead is an element, as is gold, so you can literally do it. The problem is it takes so much energy and so much cost that the gold you got out would cost more than the gold you could automatically find, so it's not really worthwhile. So we can do that, but that is one of the neat aspects of learning about nuclear physics is the only way you can change one element into another. either by nuclear reactions or by transmutations and transformations and stuff of that sort. So some of the, for instance, some of the types of reactions you can do, you could, for instance, do like Ernest Rutherford did in the, I think it was early 1900, yeah, in 1919, he observed that some of the alpha particles passing through nitrogen gas were absorbed and protons were emitted. What we ultimately discovered was that he basically had helium-4 2, which obviously helium's always 2, but this is the alpha particle. When he actually bombarded nitrogen 14-7 with those helium particles, out popped oxygen 17-8 plus a proton. That's what the 1H1 means. So by doing that, by shooting an alpha particle at nitrogen, he was able to turn nitrogen into oxygen, which, you know, that's kind of helpful. We breathe oxygen, not nitrogen. We got buttloads of nitrogen around. Let's just shoot alpha particles at all the nitrogen in the air, and we can make more oxygen. Life would be great, right? But again, that whole energy and money and all that good stuff doesn't pay off. But this is really a transmutation of an element. You literally took nitrogen and made it into oxygen. You can also do it with instead of alpha particles, you could use a nucleus, or excuse me, a neutron. So for instance, when I was at East Carolina, we had something we called the neutron howitzer, which sounds really cooler than it is. It's really just like a fat, shallow 5-gallon bucket. You know, like you've seen those orange buckets that come from Home Depot or whatever. This is about twice as large in diameter, maybe 2.5 times as large in diameter, but maybe a couple inches shorter. But it was really heavy and it was on wheels and it was a big clunk of brown metal. But if you had the key, you could actually open up the lid and then you'd look down, and in the center of that bucket, there was a vertical tube, and down in that tube was a plutonium source. I mean, plutonium, the stuff you use to make nuclear weapons, and not the original nuclear atomic weapons, but the what we call the super. So it's really a protected thing. But in it was that plutonium plus beryllium, and the plutonium, of course, would also create alpha particles, but it created neutrons as well, because it would bombard, the alpha particles would bombard the beryllium, and then the beryllium would spit out neutrons in every direction. The problem with that is neutrons are not your friends. You know, no particle radiation is really your friend. All the particle radiations can damage you. The alpha particles, at least outside of your body, are relatively harmless because they die within the, you know, first micrometers of your dead skin tissues and hairs and pieces of paper, and all that will stop them. But the neutrons, they don't act via the Coulomb force, so they just keep on trucking. So what they did, and that's why this bucket's so heavy, what they did was they took the big old bucket and filled it up with paraffin wax, which is basically just a bunch of hydrocarbons, which are known to stop neutrons pretty well. And then they left little radial tubes sticking out of it, and you could stick your sample of whatever you want radiated with neutrons. You could stick it in one of these little tubes and then put that back in the hole, leave it overnight, come back the next day, and you've now got an irradiated source. So for instance, we took aluminum and we make it into a radioactive form of aluminum. I think it was aluminum. It was either that or nickel. But either way, it made a short half-life. Actually, it made 2 different isotopes, and we could detect the half-life of both of them. But that was all from the neutron howitzer. So you could actually bombard particles with things other than alpha particles. Alpha particles are super, super densely packed, so they're kind of nice. They can do a lot of damage. But you could do them with other things as well. You can do them with neutrons. You can do them with electrons, so on and so forth. We've already learned the types of reactions that can occur, the alpha decay, the beta decay, and the gamma decay. But when you introduce something running into it, you ultimately get something quite different. And if you use different energy, so for instance, you maybe use enough energy to actually excite the nucleus, and then you can actually make that sucker get really, really large. And once it's really, really large, the strong nuclear force can't span across the whole nucleus anymore, and it ends up breaking in 2 nearly even parts. So those are some of the things that can occur. So another type of reaction we might say is we could have a neutron and let that run into nitrogen 14-7 again. So this time, instead of alpha particle, we're using a neutron, but it's still nitrogen 14.7. But in this case, when it's hit by a neutron, it gives you carbon 14.6. Again, all carbon 6, just like all nitrogen 7, but still. But it also gives you a proton. Okay, so that's another reaction that occur. And in fact, when we do these types of reactions, it saves us a lot of paper by just writing it a different way. What we'd say is 14.7N, and then we put neutron, comma, proton, comma, and 14 carbon 6. That is the same as this. So you can see you put the input thing to the left, you put the output thing to the right, and then in between you put the input thing and the output things as particles inside of parentheses, almost like coordinates. So what this is saying is a neutron combined with a nitrogen 14.7 to produce carbon 14.6 plus a proton. So that's another one. So your book does a really nice conceptual example, so I'd like to go over that. It says deuterium reaction. A neutron is observed to strike a oxygen 16.8 nucleus, and a deuteron is given off. You remember a deuteron is basically H2. That's a hydrogen nucleus that actually has 2 particles in the nucleus instead of 1, just like, in that case it's deuterium, just like tritium, which is the same thing, but it instead has 3 nucleons instead of 2. So that's what deuterium is. So a neutron is observed to strike a oxygen 16.8 nucleus, and a deuteron is given off. Is the isotope of hydrogen containing 1 proton and 1 neutron. Or excuse me, deuterium is, yeah, I've just reread what I was already saying. So what is the results? So what they're really asking you here with this conceptual example is they're saying, okay, we had a neutron that is bombarding a oxygen 16.8. I don't know why I put a fraction bar there like a crackhead, but oxygen 16.8, and that's going to combine to make what? Plus a deuterium, and of course deuterium is 2H1, right? So this is a conservation problem again. You've got to conserve certain parameters. One, we've got to conserve charge. So right now we have 8 charges. We have 8 protons, so we have 8 positive charges basically. The neutron has no charge, so whatever is over here has to have 8. So we already know for starters we got 1 proton here. So in order to have 8, we need 7 more over here. So that already gives us what our Z is, and our Z being 7 tells us it should be nitrogen, right? But the total nucleon number has to match as well. So what we had before was 1 neutron and 16 protons plus neutrons. So we had 17 nucleons total. We just lost 2 of them here, so there must be 15 here. So the product of this interaction is 15 nitrogen 7, and of course the deuterium that we already said. So that's a typical type of problem you should be able to solve. So we were given just these 2 and this, and we had to figure out what this was. And we did that with conservation of charge, which gave me what the Z was, 7. And then we used conservation of nucleon number, which is 16 plus 1. A neutron is a nucleon, so that's 17. And then on this side, we only had 2, so we had to account for the other 15, so that meant that had to be a 15. Does that make sense? All right, so that's a typical conceptual example. And as we talked about earlier, we'll learn later that's a conservation of baryon number, not necessarily just nucleon number, but that's a general conservation law that we've come up with. When you actually try to determine whether a reaction will happen, you need to know the Q value. The Q value is basically when you take, so you take all the inputs, let's say MA and MX, where A is like the little atomic particle that you're bombarding or something like that. So you say MA plus MX, and you subtract from it the outputs, which would be the itty bitty particle B, say, and the new nucleus Y, say, and you multiply all that by C squared, that's the Q value. So what we've just assumed here is that we have a particle A bombarding a nucleus X, and out pops a new nucleus Y and a new particle B. Or another way of writing that is X, A, B, Y. Either one of these could be what's going on there. Now, if this Q is less than 0, then it doesn't happen. At least doesn't happen spontaneously. Meaning on its own, okay? But you could still make it happen. You could just have to make sure this particle coming in, this A, man, I realize now I'm right off the board. So if Q is less than 0, the interaction doesn't happen. But you could still make it happen. You just have to make sure this particle comes in with enough kinetic energy that it can make the Q plus its energy greater than 0. So if this came out, for instance, the Q being negative 2 MeV, but you happen to use a 5 MeV A particle, then you could make this collision occur, or this, excuse me, nuclear reaction occur. If Q is greater than 0, it spontaneously occurs. Any questions on that? So really, what you ultimately want to do is make sure you send the particle in. If you want a certain reaction to occur, you do the total mass before minus the total mass after. If that turns out to be negative, it's going to happen. If that turns out, or excuse me, if that turns out to be positive, it's going to happen. If that turns out to be negative, then you're going to have to start amping up the energy that you shoot the particle in with. So if I shot in a neutron, I'd have to have a neutron of a certain amount of energy. And even that doesn't necessarily guarantee it, because you got to still make sure that it's going to hit the actual particle. So you've got to send in the energy. It's got to hit the actual nucleus that you want. Neutrons, which are neutral, don't naturally, obviously, interact via the Coulomb force. So that's a problem. Whereas an alpha particle, that is going to interact via the Coulomb force because that's charged. So is a proton. So is an electron. So neutrons can be quite a bit different. So let's look at an example. So let's say we have a neutron is going to be added to 10 boron 5. And this is going to be a slow neutron. So we're going to basically think the neutron as if it's going really, really slow. And then that should produce a lithium 7. And lithium, of course, is Z equals 3 plus an alpha particle. Okay? If we actually observe this to occur, even when very slow neutrons are striking the boron atom, which is also at rest for a particular reaction, in which the kinetic energy of the neutron is essentially 0, we end up getting the alpha particle. So what I have here is I know the mass of the neutron. That's 1.0087 U. I know the mass of the helium nucleus. Man, weather's getting bad here. I might lose my internet connection, guys. So if we do, we'll have to cancel lab. But anyways, if everything goes on, we'll just cancel. I'll be posting stuff via email and stuff like that. But I'm getting a pretty bad storm here. Okay, so the mass of the helium is 4.0026 U. And what we do is we observe that the actual helium nucleus leaves with a speed of 9.30 times 10 to the 6 meters per second. And what we want to determine is the kinetic energy of the lithium and the Q value of the reaction. So what we want to know is kinetic energy of the lithium and we want the Q of the reaction. But what we also know is that the that the velocity of the helium particle left with a speed of 9.60, or excuse me, I'll just leave it at that, 9.60 times 10 to the 6 meters per second. So the key point is that's, almost a factor of 100 smaller than the speed of light. The speed of light being 3 times 10 to the 8th meters per second. So at almost a factor of 100 smaller than the speed of light, then I shouldn't have to deal with relativity. I also could give you the mass of the lithium. Let's say the mass of the lithium is 7.0160. U again. Trying to separate this because I wrote everything so close together. I don't want the values running into each other, but that's the velocity. So all I want to know is what is the kinetic energy of the lithium, and what is the, got to turn my light on now, and what is the Q value for the reaction. So first off, we can do the kinetic energy of lithium. What we know is we're assuming that V of the neutron is approximately equal to 0. We're assuming the oxygen, of course, at an initial velocity of 0. In other words, just slow neutron just ran into it. So ultimately what that tells us is that momentum being conserved, that means P initial is equal to P final, suggests that 0 is equal to the mass of the lithium times the velocity of the lithium plus the mass of the helium times the velocity of the helium. So if the momentum is initially 0, which that has to be the case if the neutron and the lithium, I don't know why I wrote 0 there. This is the velocity of the lithium. If the velocity of the lithium and the velocity of, lithium, boron is what I meant. If the velocity of the neutron and the velocity of the boron were initially 0, meaning they were moving very slow, both relative to each other and relative to the lab, then the momentum before would equal 0, but momentum's conserved, so the momentum before has got to equal the momentum after, and the momentum after we know is M lithium times V lithium plus M helium times V helium. Now we also know that this is going to have to be, since it's only 2 particles, conserving momentum means that this will be a one-dimensional reaction. So I don't have to worry about X components and Y components because there's no other way except for these 2 flying off in exactly opposite directions. Therefore, they're both going along the same line. So what that tells us is that the velocity of the lithium is equal to the mass of the helium over the mass of the lithium times the velocity of the helium. It's actually the negative of that, but for kinetic energy reasons, we can just drop the negative sign. So the velocity is technically going to be the negative of all that just from solving this equation for the velocity of the lithium. So now I can say the kinetic energy of the lithium is 1/2 times the mass of the lithium times the velocity of the lithium squared, which again, I'm going to use this but drop the negative. So I'll say the mass of the helium over the mass of the lithium times the velocity of the helium. All that will be squared. We were given the velocity of the helium. That's the whole reason I'm solving that. So now I can tell what the kinetic energy of the lithium is. I can just take, and notice the mass of the lithium is going to cancel out with one of these up here. So ultimately, I just get mass of the helium squared over 2 times the mass of the lithium times the velocity of the helium squared. So that'll be 4.0026 over 2 times the lithium was 7.0160. Okay. And then times the velocity would be 9.60 times 10 to the 6th meters per second. And of course, notice this U cancels out with one of the U's up here, but I'm still left with a U. So I've got to convert that to kilograms to actually get the unit into the appropriate unit. So I know that, for instance, the 1U, so I'm going to have the extra U up there. So the 1U is equal to 1.66 times 10 to the negative 27th, if I remember correctly. Yes. Kilograms equals 1U. So that should give me all I need to do the calculation. And when I do that calculation, I'm going to get notice I didn't have to do it. I could have put this value in there twice for this. In other words, this times this to cancel out those two. And then down here, this times this again in the bottom. And I would convert all the U's, but two of them are going to cancel out anyway, so I only needed to use one. So when you see your book do something like this, sometimes they'll actually take the time to put this in there squared and another one in the bottom. I didn't do all that, and it's not necessary. So 4.0026 times 4.0026, you could have just put squared in there, obviously. This 9.60 has to be squared as well. E to the 6th. I'm going to square that, baby. And I'm going to multiply all that times 1.66. E to the negative 27. And I just did all the numerators. I did this times this times this times this times this. Now I got to divide it by 2 times the other thing. So I'll say divide by parenthesis 2 times. If you don't use that parenthesis, your calculator is going to realize that dividing by 2 times 7.016 means divide by 2 and then multiply the answer by 7. So make sure you do that. Ultimately, my answer is 1.74. I might as well call this 747. And that actually goes for quite a few decimal places, times 10 to the negative 13 joules. So that's 1.747 times 10 to the negative 13. I know you can't read that very well, but that's basically what the kinetic energy of the lithium is. I should convert that to MeV, say. So I know that I can divide that by 1.602. E to the negative 19, and that'll give me EV. And I get 1.09032 times 10 to the 6th, so that's a mega electron volt. So I'm going to say 1.09032 mega electron volts. That's the kinetic energy of the lithium. And it also wanted to know the Q value. So we can take that as well. We could also figure out, of course, all the kinetic energies of everything and all that good stuff. And we're going to ultimately need to do that to figure out, hence, how much energy is going to take. But basically, the Q value is always going to be the kinetic energy, or excuse me, the masses initially minus the masses finally times C squared. That's the reaction or Q value energy.
Professor,
Yes.
for class, could you like post the notes because it's a little blurry? That's the bandwidth is low.
I've tried to do that, and I'm just not that capable of doing it. But what I'll do is I'll show it again on here, up close, and that way, when you're watching the video, you should be able to pause it for a second and copy anything you miss. But yeah, keep doing that. Ask me to, whenever it happens like that, ask me to show you again or something like that. I haven't found a way. Well, I found a way. I mean, I can take pictures all day long and post them. But what happens is I run out of memory on Canvas really quickly with photographs. Because when I share videos on YouTube or on Studio or something like that, that's not stored on our Canvas page. and they won't allow me but for so much extension of memory. And when I go over, it actually costs the school money. So I haven't been able to find a way to do that efficiently. So I'll just keep doing what I just showed you, is try to put all the numbers in a way that you can read them. And then you'll have a chance to actually pause it on the video. Sorry about that. I hope that helps though. All right, so we've got all this worked out, but we still need to know the Q value. And we also need to know, how did this actually occur? Because if you read the example, I did an example sort of like the one in the book. I changed the kinetic energy a little bit, but basically, or changed the speed of the alpha particle a little bit. It said the nuclear reaction of a neutron with 10 boron 5 yields 7 lithium 3 or lithium 7-3 plus a helium nucleus, which is helium 4-2. It's observed to occur even when very slow moving neutrons strike boron, the boron atom at rest. For a particular reaction in which the kinetic energy is approximately equal to 0, the outgoing helium, and it gave me its mass, is observed to have a speed, and this is what I changed. I changed it to 9.60 times 10 to the 6 meters per second. Determine A, the kinetic energy of the lithium, and B, the Q value of the reaction. But since the boron and neutron are both initially at rest, that gave us that the final potential energy, or excuse me, the final momentum of the lithium has got to equal the final momentum of the helium, just in opposite directions, which is why that negative sign appeared earlier. So when we solve that, we can actually use it to compute the lithium's kinetic energy, which we just did. And we found the lithium, instead of like your book's example where it came up with about 1.02 MeV, in our case, we came up with about 1.09 MeV for the lithium, because we gave our alpha particle a little bit more energy. If we want to know now what is the Q value, we're given the data that basically the kinetic energy of the neutron equals the kinetic energy of the boron equals 0. So the total Q value has to be equal to the kinetic energy of the lithium plus the kinetic energy of the helium. So another way we could actually do this is just now go ahead and calculate the value of the kinetic energy, and we'll get the kinetic energy of helium. When we add that to the kinetic energy of the lithium, then we'll know the total Q value. So let's do that now. The kinetic energy of the helium is actually equal to 1/2 the mass of the helium times the velocity of the helium squared. Well, that's going to be 1/2 the mass of the helium, turns out to be 4.0026. And this is the only place we're going to use it, so I'm going to go ahead and put the conversion in there, 1.66 times 10 to the negative 27th kilograms per U. And then times 9.60 times 10 to the 6 meters per second squared. When I compute all that, and again, I'll bring this closer to the screen in a second, or closer to the camera in a second. So I'm doing 0.5 times 4.0026 times 1.66 e to the negative 27 times 9.6 e to the 6 squared. And it looks like I typed everything correctly. I get 3.0617 times 10 to the negative 13 joules. Again, converting that to electron volts, I'm going to divide by 1.602 e to the negative, or excuse me, e to the negative 19. I get 1.91117. I'm just keeping a bunch of extra digits. Obviously, I'm not obeying significant digit rules, in other words. Times 10 to the 6 EV. So that's 1.9112, say, mega electron volts. So in principle, the Q value for this has to be equal to the total energy difference. Well, the total energy difference has to be equal to the kinetic energies that the particles came out with. So that's why I'm saying Q is actually equal to all this. So I'll say Q is equal to, we had earlier calculated 1.09032 MeV for the kinetic energy of the lithium. I'm going to now add to that 1.91117 MeV for the kinetic energy of the helium. This one, I don't know why I've got a dot there, but the decimal's there. So 1.09032, that's 5 sig fig, or 5 decimal places, and this is 5 decimal places. I'm going to add them up, say plus 1.09032. So I get roughly 3. I don't know why I didn't just do that by hand, but anyway, it's 3.0015 mega electron volts. So that's the Q value. Remember, the reason why we were able to do this from the Q values, or from the kinetic energies, as opposed to doing all the masses, which I could have done, was basically that the Q was supposed to be the mass of the neutron plus the mass of the lithium, or excuse me, of the boron, minus the mass of the alpha particle, minus the mass of the lithium, all that times c squared. So this accounts for basically all the energy, or all the mass that stayed as mass. Everything else had to become energy. And that energy, unless one of these nuclei were in excited state afterwards, which they weren't because they didn't tell us they were, all the energy has to go into kinetic energy of the product. So that actually has to be equal to the kinetic energy of the lithium plus the kinetic energy of the helium, which is what we just calculated. So if you want to go back and try to work this out with the mass of the neutron and all this stuff and do the c squared, really remember, you're not really multiplying by c squared. You're just going to take the u and realize that the u is 900 and I think it was 31.5 MeV per c squared. You use that conversion, and then you're automatically, by multiplying by c squared, you're just canceling out the c in the bottom, and you're converting the mass instantly to energy. So you can see all that occurring. Let me again show you this just in case. So this is all the math we did for that problem, all the numbers. Go slowly across. And that should give you plenty of time to actually pause that. So that's a typical example of what might happen with a slow neutron. They can ask you questions like, if you look at your textbook, there's example 31.3, where basically they're going to ask you whether an actual reaction will go. They say, will the reaction go? And they ask you about basically a proton bombarding a carbon 13.6 and producing a nitrogen 13.7 and a neutron. And they say when it's bombarded, the protons actually have a 2.0 MeV energy associated with it. So that means basically the kinetic energy of that thing is 2.0 MeV. So all you're going to do with that type of example, let me do it. Let's say P plus 13 carbon 6 yields 13 carbon 7, or 13 nitrogen 7, sorry, plus a neutron. And this guy has kinetic energy equal to 2.0 MeV. So all you have to do to find out whether this will go is you're going to calculate Q. Well, Q is going to be equal to the mass of the proton plus the mass of the 13 carbon minus the mass of the neutron minus the mass of the 13 nitrogen times c squared, and that's going to give you a value. That value in energy, if it turns out to be negative, then it wouldn't occur by itself. But if it turns out to be negative but smaller than 2.0, then we've got enough energy for it to happen. Therefore, it will occur. If, however, it's negative but the number's bigger than 2.0, then we got issues. So when we calculate this Q, it turns out our difference in energy is going to basically be 14.011180. I think it's 14.01. Yeah, sorry. 14.011180 minus 14.014404. Okay, so you see what ultimately happens is I've got a 14.011 minus a 14.014. That's clearly going to be negative, and because it's negative, we're going to have a Q value that is negative, and the reaction won't occur unless the proton's bringing enough kinetic energy. Well, when I do that math, when I subtract these two values, I get 0.003224. And if I multiply, that's a U, not an A. Let's just scratch it out, put a U. Okay, now if I take this 0.003224 U and multiply it by the conversion factor, 931.5 MeV per C squared per U, then I will get a 3.00 MeV for the energy. Okay, so when I did this plus this, I got 14.011180. When I did this plus this, I got 14.014404. All of that times C squared would be the Q. When I did that subtraction, I got 0.003224 U. So I convert that to MeV per C squared. And 931.5 MeV per C squared is equal to 1 U. So that cancels out the U. So I ended up getting 3.00 MeV. So what this means is all of this came out to be negative. So really, if I'm going to set this equal, I just said this was sort of delta Q magnitude. It turned out to be negative, which we could tell from that. Since its magnitude was actually larger than the 2 MeV, we know no, the reaction will not occur. Okay, so that's more or less what this entire chapter is about, is can you, or at least the mathematics aspects of these chapters, is can you actually calculate whether a reaction will occur or not. So it turns out there's actually ways where you can actually create reactions that you want. So for instance, normally when something just decays, it either decays by alpha decay, beta decay, of course electron capture is part of that, or gamma decay. But you can actually spontaneously cause reactions by throwing in alpha particles, neutrons, electrons, all sorts of cool stuff. But what if you wanted something to break down other than just by alpha, beta, or gamma? What can you do then? Well, it turns out if you use the liquid drop model of the nucleus, which is actually a model that Bohr worked on for his PhD, you can sort of take on individual particles, and when a particle comes in, that just creates a vibrational energy of a liquid drop, and it causes it to vibrate and stretch and stuff like that. When you do that, you have a nucleus that's initially sort of spherical. Of course, it's a quantum thing, so it's got an electron cloud, but there's sort of some distance at which you could say the majority of all the probability is 99.99% of finding it within some radius. Then you treat the nucleus as if it's a sphere, but when you bombard it, it's going to start to vibrate all sorts of different ways. So it might even get in that shape, then it might be doing this shape a little bit. And it might even be doing this shape where it's in and out as opposed to something like that. But ultimately, if it gets far enough apart, then the nuclear force, which we told you is sort of like Velcro, it's very strong when they're right next to each other, but it has no effect whatsoever when it's over a certain distance away. Then out pops two nuclei that are comparable in size. This is called fission. So this is how we work nuclear reactors. This is also how the first atomic bomb was built. Basically, we were trying to make a critical mass where basically you got enough, a neutron comes in, it bombards a uranium nucleus. That uranium nucleus creates more neutrons when it broke apart, such that those neutrons could go on and cause other uranium nuclei to break apart, such that those could break apart. So you got a chain reaction, and each one letting off on the order of, I think it's a couple hundred MeV per reaction. And that would happen in such a small period of time that it would release a great deal of energy in a small period of time, and that was a nuclear explosion. In order to do that, though, we had to use a very specific isotope of uranium. It was uranium-235, and we had to have it over 80% pure. Whereas in a nuclear fission reaction like we have for nuclear reactors, we can use 8% up to 20%, and that's plenty good. And some of them can even be used where you use the product of that to make a new reactor with a new element. So there's a lot of pluses and minuses to it. So that's sort of the crux of the next material, is talking about what happens when a neutron, for instance, bombards uranium-235. So let's say we have a neutron. It's going to bombard uranium-235. It might help you to remember that uranium is 92. That's the highest element that's naturally occurring. After that became neptunium, that was discovered, and that was 93. And of course, this is not something that naturally occurs on Earth. You can produce it in nuclear reactions, but that's about it. And then that's neptunium, and then 94 is plutonium. Okay, but if you bombard this with a certain amount of energy, specifically high energy neutrons and stuff like that, maybe you can actually set up these weird oscillations that can ultimately produce fission, which is where one nucleus breaks up into two nuclei. When two nuclei come together to make one, that's the opposite, and that's called fusion. This is called fission. And this is what reactors use. So nuclear submarines and stuff like that, they use those. This will actually normally incite a decay into 236-92 uranium. So in other words, the electron just became part of the nucleus, but that's not a stable situation. The uranium-236 is radioactive. It doesn't last for very long. So what you normally get is two daughter nuclei, X1 and X2, say, plus some number of neutrons. So that's normally what happens when you bombard nucleus, a uranium-235 nucleus, with a neutron. The compound nucleus, by the way, this guy right here, only lasts for about 10 to the negative 12 seconds. So it's a very quick process, basically going from here, a split second here, and then to here. The two fission fragments are rarely split into uranium, split the uranium in half. It's normally like a 50-60 thing or 40-60 thing, where this one will have 40% of the mass and this one will have 60% or vice versa. So one process, for instance, is you can have the neutron bombards 235 uranium, and that produces 141 barium plus 92 krypton. I'm hoping I'm remembering all my elements correctly. But that also yields 3 neutrons. Okay. I can go ahead and put these numbers down here just so you don't have to look them up. The barium is 56 and the krypton is 36. So this is a typical reaction. If you wanted to have that, you could actually calculate the Q value, all that good stuff. But really, it turns out when you bombard uranium-235 with neutrons, what you find out, or actually any number A, basically, if you make a plot of A versus the energy percentage, you end up getting this neat graph that looks like M, like that. And basically what happens is this is when the nucleus actually breaks up exactly in half. That, as you can tell, only occurs around, this is in percent and this is 0.01. So about 1/100th of a percent of the time, you'll get it split up exactly in half. The vast majority of stuff happens right around here, and this is on the order of 8% roughly. Okay. So this is 160. This is around 75. And this is around 118, something like that. So that's normally what happens is, yeah, you get, you know, one nucleus that's on the order of 40% and another nucleus on the order of 60%, that sort of thing. That's the much more normal occurrence. So with that, you can now start to talk about nuclear reactions in general and nuclear reactors. For instance, your book has the photograph of the only photograph. This is literally a copy of the only photograph that exists from University of Chicago. So what happened was Enrico Fermi, he's probably, well, I heard one person say one time that the Swedes are the reason we won World War II. That's a sort of bold claim, but hear me out. His idea was this: the Swedes awarded Enrico Fermi the Nobel Prize. At the time, Mussolini was the leader of Italy, and he ran a tight ship. The good news was Enrico Fermi was brilliant. So he sort of didn't mess with him. He just let him do his science thing, and even put him ahead of many committees and stuff like that. But when he won the Nobel Prize, that's a great honor for a very small country that Italy was, and they hadn't been much since, you know, the days of Rome. So he was really in a bit of a conundrum. Do I let this guy go to Sweden or to accept the Nobel Prize? And they decided to let him. Well, when he did, he immediately defected, and he had managed to talk them into letting him take his family, which was the big thing. Normally, you'd leave your family behind because the state didn't want you to leave, but he was able to take his family, so he immediately defected to the U.S. The U.S. gave him a job at the University of Chicago, which is still to this date one of the most awesome universities ever in existence, at least from a physics standpoint and law standpoint. But it was really elite, and he sort of made it elite. But that's where Fermi Lab is and stuff like that. So what he did was created a nuclear reactor. Basically, he used this theory to try to create a nuclear reactor, and he built it under the football stadium at the University of Chicago, and figure 31.6 in your textbook is a photograph of that. So that was called a pile, which is the same thing we used earlier. Remember I told you about a pile being what they call batteries? So that was called a pile, and he actually discovered, he was working under Arthur Compton, who we talked about in quantum mechanics. He, at least from a government standpoint, he was working under Compton. But he actually was able to get a chain reaction to occur to generate energy. And the secret message that was sent to Washington via telephone was the Italian navigator just landed in the New World. And what that meant was, hey, he's actually split the nucleus in a robust way that was able to be controlled with cadmium rods and stuff of that sort. So that was a really big deal. The other problem was the greatest power right then at that time, other than Enrico Fermi and a few physicists that America had, as well as some few physicists that America had stolen from other countries. Basically, the superpower, other than those three, were essentially got a weather warning. The other superpower was in fact Germany. Ooh, having a storm surge warning. So the other power was Germany. Well, that's kind of a problem because I don't know if you know it, but during World War II, Germany was kind of wreaking havoc on the world. They had invaded various countries, and that was, you know, they even took over the Vatican and stuff like that. So that Poland they invaded and so on and so forth. So the last thing anybody wanted, including various high-ranking scientists within the German government, the last thing they wanted was Hitler having a nuclear weapon. And everybody knew the physics was pretty straightforward, that if you can get a nuclear reaction to occur, if you can split open a uranium nucleus using, say, one neutron, and then that produce more than one neutron, then that'll split another uranium nucleus. In fact, it'll split probably two, and then each of those will probably split two, and each of those will split two, and each of those will split two. That is a exponential growth, and basically that's one of those things where you know essentially an infinite amount of energy could come, and that's theoretical, of course. So it would basically cause all the nuclei to react in a small period of time, releasing so much energy that we would have a weapon that was tens of thousands, if not hundreds of thousands times more powerful than all the other weapons we had. We already knew that the uranium as a power source, which is what Fermi had worked on, was going to give us per say kilogram of uranium, we're going to get on the order of 10,000 times more energy than per kilogram of carbon. So that was already a big deal. So we knew we had these energy constraints. But the other thing really was beyond the nuclear reactors, we can now make a weapon. So Leo Szilard, S-Z-I-L-A-R-D, and a couple other people got together and approached Einstein, who by this time had been quite famous, and pretty much everybody listened to what Einstein said. So they wrote a letter and got Einstein to also sign the letter, and they sent it to the president at the time, Roosevelt. And in doing so, they convinced Roosevelt that yes, Germany had the power to create a nuclear weapon. They had the know-how, they had the brilliant scientists that were necessary, and that we had better beat them to it and keep them from doing it. So that actually did happen. They created a project called the Manhattan Project. Leslie Groves, who had handled really, really huge projects in the Army, General Leslie Groves was in charge of it. He talked to all the people in the basically in the scientific community, and hands down, everyone said, you need to get J. Robert Oppenheimer. So J. Robert Oppenheimer, who has a sordid past, I definitely recommend you read the book American Prometheus. He sympathized with communism, as did a lot of intellectuals at the time. Every one of his undergrad or every one of his graduate students did. For instance, his brother did. Enrico Fermi sort of did to some extent, because you know he just came from a communist country, Italy. So it was a really big deal. But he told Groves, he said, "I don't think you want me in part of this." He said, "Because I'm sort of been sympathetic to communism." And Groves said, "Well, are you now?" He said, "No, I've sort of realized the end game is really bad. I still have friends in that area, and if I go off somewhere, I won't be interacting with them." He said, "But I'm not a card-carrying communist, but I certainly have some communist background that might cause you problems." And Groves said, "Don't worry about it. I'll take care of it." So J. Robert Oppenheimer headed the Manhattan Project. He had people like Enrico Fermi and Niels Bohr, and Niels' son Aga Bohr would come on from time to time and give him advice and stuff like that, which was really amazing because this is a top secret program going off in Los Alamos, New Mexico. We had Oak Ridge, Tennessee was doing a part of it as well. We had other labs up in Chicago doing parts. And all the great scientists went there. Hans Bethe was one of them. H-A-N-S is his first name, and B-E-T-H-E is his last name. They called him Beta because he was sort of like at least the second best at everything. So he was an amazing dude. He's the one that discovered the nuclear reactions that large mass stars go through. You'll see that in section, I think, 31.4. That's called the CNO the carbon, nitrogen, oxygen cycle. The CNO cycle basically is a way that a large mass star can quickly fuse hydrogen and helium. The proton-proton pair is another one, or the proton-proton chain is another one, but Hans Bethe didn't do that. But all these people, Richard Feynman, Wheeler, all these people went to the Manhattan Project. Feynman was like 17. He, literally was working on his PhD at the age of 16. He went to MIT at the age of like 14 or something. But anyways, he's working on his PhD at Princeton under Wheeler. He had just gotten his bachelor's degree from MIT, went there, and he ended up getting sent out to Los Alamos. All the equipment was sent all over the place. Oppenheimer was super, super wealthy. He owned an island, for instance, in the Caribbean. But him and his family were super wealthy. And they knew of this land out in New Mexico that would be so secluded. It was one of his childhood places where he played and rode horses and stuff like that. So he got the government to buy a big chunk of land. They made a huge national laboratory out there. And then they put all these scientists, these Nobel Prize winning scientists, sitting around a table wearing shorts and what they called shirt sleeves, which is basically a collared shirt with short sleeves, eating bologna sandwiches and solving physics problems. And the movie Fat Man and Little Boy is a good representation of that. The American Prometheus book is an excellent representation of that. Surely You Must Be Joking, Mr. Feynman tells another excellent story about it from Feynman's standpoint, including Bethe and people like that. But ultimately, it was an engineering problem. It wasn't a physics problem, but physicists are notoriously good at being able to solve problems, period. Perhaps if you had the right kind of nuclear, right type of engineers at the time, they could have done it a little quicker, but such engineers didn't exist, so they had to make up the engineering as they were going. So the engineers put together all this product, and ultimately they discovered a way to make a nuclear weapon. During the meantime, another physicist that was working on the product got really excited to try to make a nuclear weapon, and discovered there was one that could even though this one was 10,000 to 100,000 times more powerful than conventional weapons, he discovered, in fact, that there was another weapon that you could make that would be another 10,000 to 100,000 times more powerful even than that, and that's the thermonuclear weapons that we use nowadays. They were working on the atom bomb, which is a fission device. He had discovered the super, is what they called it, and that would be a fusion device, and it would actually use the nuclear weapons like we used in Hiroshima and Nagasaki and the Trinity test. It would use those nuclear weapons as a detonator for this more powerful nuclear weapon. So that was sort of what happened. About this time, Oppenheimer, who was this brilliant polyglot, he taught himself Sanskrit so he could read the Bhagavad Gita and the Upanishads. He also taught himself Swedish and all these other different languages. He's really a brilliant dude, knew like 12 languages or something. He was starting to get the idea that he knew for a fact Germany was failing. They were not able to get a bomb. He knew that this bomb was even more terrible than he thought, and he started having second thoughts about wanting to drop it anywhere. But of course, he had already signed a contract, and he knew it wasn't his decision to make. But at the same time, he wanted people to see a real demonstration of how horrible it was. And ultimately, he was giving a list of cities, and then he went and chose the one that would make the most horrendous site possible in hopes that no one would ever use a nuclear weapon again. He knew exactly the blast radius and how big of buildings and things that could be blown apart. And he knew how to do it the worst possible way so that it'd be, literally would flatten it. So he chose Hiroshima and Nagasaki specifically because their radius of that town, if you picture it sort of like a city, like a circle, the radius of those towns was just slightly larger than the blast radius of the nuclear weapon. So if you drop that in the center of such a town, then it'll literally leave this gaping hole in the town, and that will, people flying over have that image, and they will, forever see how awful this is. Not only that, he did so by detonating it, several hundred feet above the ground, because that would actually cause competing shock waves. The shock wave that would first get to the buildings would push them down and away from the bomb. Then a second shock wave would bounce off the ground and push it up and away. In fact, ensuring that the buildings would be destroyed. It was really a horrible thing, but yeah, that was the only thing he could think about it. And he was pretty much depressed for the rest of his life, had a really miserable life. Plus, he had a horrible case of cancer because he literally smoked, one cigarette, lit off the other one day and night, constantly just smoking. I think he ended up dying of lung cancer at a quite young age. He went to the president, Truman, and told him, he said, I have blood on my hands. And Truman said, don't ever let me see that son of a bitch again. I don't want to see his sorry face, because, he had actually ordered the weapon to be dropped. So he obviously had more blood on his hands than Oppenheimer had. So anyways, it's just a tragedy, great discovery, brilliance, and all this stuff come together to make something really, really horrible. But in the end, I guess somewhat necessary. It's kept us safe for a long time. Now other countries are using it to keep them safe. It's released energy. Some of the cleanest possible energy we could use is nuclear energy. So that pretty much covers it. If you look in section 31.3, you'll learn about plasma accelerators. You'll learn about inertial confinement. And if you read on through 31.4 and 31.5, you'll find out about the Becquerel, which I've already introduced you to, and the Curie, which I've already introduced you to. And you'll read more about human exposure. There's things called the gray, that's an absorption dose. There's a thing called a Rankine, ROENTGEN. And these are all measures of nuclear, or basically of energy radiation damage that is important to medicine. You'll learn sort of like the Coulomb law, how when you double your distance away from a charged particle, you decrease the force by a factor of 4. That's the same thing when you have a small radioactive source. If you double your distance away from the radioactive source, you decrease your dosage of radiation by a factor of 4. Whereas if you shorten the amount of time you're around it by a factor of 2, in other words, you could spend 2 minutes, but instead you're only going to spend 1, you might think that's a safer thing than doubling your distance, when in fact you'd be wrong, because doubling or cutting your time around the radioactive source in half only decreases your radiation dose by 2, whereas doubling your distance away decreases your radiation dose by a factor of 4. So those are all really interesting and helpful things to know. If you look on page 904, you'll even see the Bragg peaks that I told you about regarding the proton therapy. So proton therapy is really wonderful. It has this narrow spike of relative dose that you can control how deep it goes into the tissue. And then, of course, the peak would be ideally right in the center of the tumor. And then beyond the tumor, where the more important parts of your body are, very little radiation will happen. They tell you about how they allow the radiation source to approach the tumor from various directions. So there really is a lot of good stuff in here, but it's mostly of a practical use in terms of understanding stuff. If you go into, for instance, radiology or cancer therapy or any medical field, or anywhere that ends up using radioactive things, like if you're in a plant that builds, let's say, smoke detectors, you're going to be dealing with a nuclear source, americium probably. If you work on, say, roads, they have a radioactive source they use to penetrate the ground to see how hard and what's below them. That's another possible thing. So it actually turns out to be a lot of places. And then you just need to know a little bit about radiation anyways, just to know why radon's dangerous and stuff like that. So I think that pretty much covers all of chapter 31. Does anyone have any questions for me? I want to switch back to the regular camera, to the webcam. So I didn't go with a lot of specifics on those last things that we were just talking about, the Becquerel, the Curie, the Gray, the Rankine, and all those things. But there's REMS too, REM, all that stuff is relevant. The figure that I keep in mind is you're allowed 5,000 REM per year to your gonads. That's what the standard is. 5,000 REM, or excuse me, millirem, or 5 REM to your gonads. And they use gonads because that's the part that's most sensitive to radiation damage. So they're talking about your, if you're female, your uterus, and specifically more so your ovaries. And for us dudes, that would be the testicle areas and that sort of stuff. Those areas are most sensitive to radiation damage. And basically you're allowed 5 rem per year as a regular person. Okay. If you exceed that, you really need to be a person that's has a badge. And that, in fact, if you're coming anywhere near that, you should have a radiation badge that you wear every day that is sent off usually every quarter, say every 3 months. Sometimes they only send them once a year, but really every quarter is probably a better scenario, or at least every half year. But they send it off and tell what your total radiation dose has been since the last time they checked it. And that allows them to keep an eye on you. So if you start reaching that 5 rem number, or excuse me, 5 rem or 5,000 millirem number, then they'll say, okay, well, it's time for you to take a break. We're going to put you in the office for a little while. So people that run x-rays, people that inject me, for instance, with that technetium 90, or people that fed me that technetium 99, those type people wear those badges. I worked at an accelerator lab. People that work at Jefferson Laboratory, for instance, they will generally wear those badges all the time, and that keeps track of you. So those are important things to keep in mind. And just reading this chapter, especially if you read the whole chapter, you'll get a much better understanding of radiation, and hopefully not be one of those people that's just generally scared of it. Like, you probably know radiation now. You should understand that radiation is just normally just an electromagnetic wave. It's electric waves orbiting or oscillating one direction, and a magnetic field oscillating the other direction, while the two of them are traveling along at some mutually perpendicular direction. That's really what radiation is. Then there's particle radiation, which is the alpha particles, the beta particles, and the gamma radiation. The alpha particles outside of your body are essentially harmless because they can't penetrate much. But the other ones, the beta is electrons, they can do some damage. All of them can do damage if you give them enough energy. And the gammas are really bad because they can go through everything, and they're photons, so they're not really charged, so it's not easy to stop them. Sometimes that's a plus. If they're so energetic, they just go right through you, then they don't damage anything. That's the case with neutrinos, and we have like 10 to the 22 of those going through us every second. So anyways, it seems like no one has any questions. Is that correct? All right, do y'all need a break, or you want to just go ahead and start into our lab then? Maybe 5 minutes or something like that?
Yeah, a 5-minute break would be nice.
Okay, so let's meet back at let's say 12:05. I'll go ahead and kill this this Zoom meeting and open up the other one, and we'll get started on the lab. Okay, see you folks.